Alrighty, welcome back everybody. This is our fourth lesson in our series of linear relation stuff here, where we're going to be talking about functions. Now, you might have heard about functions or relations in general before. Now, functions are very specific and they follow a rigid set of rules. So we'll look at a couple of relationships here first. Now, they are categorized by being functions and non-functions. So there's something similar about all the functions and there's something similar about all the non-functions. So if I were to look at these, and the top ones, it does straight up tell me that these definitely are functions. And the way that you can look at them, everything's kind of unique. So all of my x's here look like they're unique. 1, 2, 3, 4, 5. 2, 4, 6, 8. Those are all unique x's. In this first graph here, there's a bunch of unique x's going, left to right as the x's do. Same for pretty much all of them. But the things that are non-functions is where you're going to start to see something change. You're going to start to see repetition in our x's. So 12s, those are all repeated x's. In my circle, I might have a coordinate pair that might have the same x values. Right? So if there's that one's 2, so the x value of 2 might have a y value of, 5 above the top. Now, my x value of 2 might also have a value of negative 5 underneath, and we see that becomes an issue. Same thing for all these graphs. I'm going to see the same x values, in multiple places, in multiple points. That's going to be the difference between things that are functions and things that are not functions. So a function is really going to be that special type of relation where each element in the independent variable, so every element in the domain set, is associated with exactly one element in the dependent variable, or the range. Okay, so we're going to see one-to-one relationship here. Now, if we go to identify some of these things that might be functions or not, we can really take a look at what kind of happens. Sometimes it's difficult where things aren't actually numerical all the time. You might not be given explicitly your input of x, your output of y, but we can see if the relationship actually makes sense. So a relation that associates given shapes with the number of right angles in the shape. So we've got right triangles of 1, acute triangles, 0 right angles, a square has 4 right angles, a rectangle also 4, regular hexagon 0. So taking a look at that relationship, we can talk about this a couple ways. So one, this absolutely is a function. Okay, so it definitely is, since each shape has a certain number of right angles. It absolutely is a function. You can write this out splitting up the domain from the range. So the domain is going to be the set of the shapes. Right triangle. We have acute triangles. Acute. We've got squares. We've got rectangles. And we've got a hexagon. Okay, that's the set of our domain, the set of our inputs. Now our range will be the number of right triangles actually associated with these shapes. So we could have no right angles, we could have 1 right angle, or we could have 4. Really, those are the only choices for that output. If I look at B, just figuring out if this is a function or not, we are told that the first set is going to be the square of the second set. So 1, for example, is the square of both negative 1 and positive 1. If I take negative 1 and I square it, I get positive 1 and square it, you get positive 1 again. So that's how this is working. So 4, you can see, could either be negative 2 or 2. 9 is negative 3. Now 3 isn't actually represented in this set. I'm really only looking at these elements, these pieces. Now, even though that relationship is a true one, if I square one thing, I get the other, that relationship does not represent a function. So that is not, I should say it's not a function. Okay, and the reason why is the input of 1, right? It's got 2 outputs, right? That input of 1 could really be going to negative 1 or positive 1, but we're not actually told which one I should use. That gives us a problem. So the input of 1 has 2 outputs. it could either be -1 or 1. Now our calculators, when we take the square root of 1, it never tells us it's -1. It only tells us it's +1. It's only really telling us what we call the principal root. Okay, your calculator is not telling you what the other root is. Even though it exists, it doesn't actually give us with a function because of that ambiguity in what could the square root actually be. So that gives us a problem. Now, there's an easy way to check if a graph is a function, and that's called the vertical line test. So underneath you can see that it says that a graph represents a function when no 2 points on that graph lie on the same vertical line. The reason why we use vertical lines is because they go through one unique value of x. If your graph crosses 2 points on that graph, that means that x value that's associated with that vertical line occurs in 2 distinct places. So in order for something to be a function, that vertical line should only be crossing your graph 1 time. If it crosses twice like it does in a circle, you can see that x value associated with the vertical line, that the x value of it is 2, but it's got 2 y values, either 4 or -4. That means it's not a function. Okay, it's got to be that unique 1-to-1 relationship with those inputs and outputs. Okay. So we can determine whether or not each relation is a function by looking at the inputs and the outputs. So if I look at A here, that absolutely is a function. And you could say that each input only has one output. Each input only one output. Okay, so if you were to draw a vertical line somewhere, you could test this out. I can draw that vertical line and I can move it to clearly show that yes, it passes that vertical line test. It will only cross at 1 point, no matter where I place it. Okay, so we'll keep that line handy. We'll use it in a couple places. Now, obviously, for that circle there, if I were to use that vertical line test again, you would see that, oh wait, that vertical line happens to cross my graph in more than one place. So let's say the x value is 2. You can see there's 2 distinct y values associated with that one input of 2. So this would mean that this is not a function. Okay, so this is not a function because the input of 2, let's say the input of +2, has outputs. I'm having troubles writing today. It has outputs of, you will see that it's at 4 or -4. So since that input of 2 has distinct outputs, there's 2 different ones, you're going to say that that is not a function. Okay. You can do something similar if it's a discrete bunch of data. Now if I drew a vertical line through that one, you can see that the input of 3 corresponds to multiple outputs. Okay, way too many for this to be a function. So this is not, since the input of 3 has multiple outputs. Okay, not a function. Now I guess I'll keep that vertical line. I might have actually blocked the graph with my face there, so let's just show that again. So that vertical line, since it does cross through all of those, even at the input of 2 or the input of 1, I've got multiple points on the same input. So that doesn't really make it, that's not a good thing. That makes it not a function. If I go jump to F here, there again you can see that vertical line crossing twice. So for the same reasoning as the other 2 that weren't functions up above, we'll say that one is also not a function because you have one input corresponding to multiple outputs. Okay, so we'll call that quits for our vertical line there. Okay, if we look at D, we've got a table of values here this time. So we're really trying to look for a place where I have, the same input going to 2 different outputs. And you can clearly see that in the first one, you've got, your inputs of 1, happens in 2 places, but the y values are both different. Okay? So this one also not a function. You have the input of 1 going to multiple outputs. Okay. If you look at E, you've got a list of coordinate pairs. So let's see if we've got any repeated inputs. So I've got 2, 4, 6, and 8. That is absolutely okay. even though you're going to see some outputs that are the same. That means 4 as an input goes to -1, but 8 as an input also goes to -1. Since those inputs are different, that is okay having the same output. That's fine. So each input has one output. Okay, it's okay if that output shows up multiple times. You need the inputs to be unique. Now I always like to give like an example where this actually has real life context. Let's assume that you're going to the store and you're buying a shirt. Right? Let's say that shirt costs $25. If you go to one cashier, they charge you the $25 the shirt's supposed to be, but the other cashier that you might try to go to might charge you $30 for that shirt. Now you might be thinking, well, that obviously doesn't make sense. Why would one person charge me more than what the shirt costs versus the other person charging me what it actually costs? Right? The input here is the fact that the shirt is $25. Right? It's the shirt itself. That shirt can't cost different things going to different people. That doesn't make sense for that business. That would not be an example of a function, since those outputs are different, not a function. So keep that example in mind when you try to distinguish things. Okay, if you're asked to identify whether a graph is a function or not, really what you're going to try to look for is that obviously that vertical line test. See if you have a repeated x, repeated input going to multiple outputs. So the first one is talking about shoe sizes here. This would not be a function. Okay, so not a function. As you can see that the shoe size of 9 is repeated for different heights. So even though somebody is taller than you are, you might have the same shoe size, is what this really says. But this fails the vertical line test, because that vertical line would go through all of those points. Okay, the shoe size of 9 does not guarantee you have a unique height. Right? People could be different heights and have the same shoe size. World population. That has to be a function. Okay, for any given year, there is only one answer for the global population. In 1950, it was just over 2 billion. Right? It's not also going to be 4 billion because that would mean I had two different populations in the same year. That just doesn't make sense. So this one has to also be a function. And again, it also passes the vertical line test. Each input of the years corresponds to a unique output of the global population. Now, this might take a little bit of a different turn when we go to talk about function notation. So all it really is a new way of writing an equation, but now we know for sure that that is really representing something that is a function, not just a generic relation. Okay, so a function notation, new way of writing an equation. We're used to seeing our input as x, output of y. Now we're going to give our equation special names like f and g. They will help us distinguish between different equations, help and allow us to see inputs more clearly. Now, really what that f of x means, it really represents your output of y. Now students always get confused between, why does it say f of x now? Am I taking f and multiplying it by x or something? No, that's not really what it means. We're really saying that 10x minus 8 is a function and its input is x. Really, that's what we're saying here. So if I take this function 10x minus 8 and I let the input now be positive 2, I'm going to input that number in for x. So this would then say my function, when the input is 2, really means it's 10 multiplied by that input of 2 minus 8. Okay, so that really just gives us 20 minus 8, which is 12. So really all this does is now really tells us, okay, take your function, make the input 2, figure out what the output is. So really, f at 2 is equal to 12. Or as a coordinate pair, that might tell somebody it's the input of 2, because that's what x is, f of x, right? So the input of 2, output of 12. Really, these mean the same thing. So I'm just going to do a couple of these because, they end up being quite repetitive. So I'm not going to do the second one because I'm just putting in a negative. We will talk about 3, because now I don't know what the input is. I do know what the output is, and the output is 42. If I keep the original function, f of x is really 10x minus 8. I'm told now that f of x is equal to 42. I know what the output is. So I'm going to take my 10x minus 8. I was originally told that's what f of x was. If I make it equal to 42, because again, f of x is also 42, now we can solve that resulting equation. Add 8 to both sides, so 10x is going to be equal to 50. Dividing both sides by 10 leads us to figure out that when the value of the function is equal to 42, the input must be 5. Okay, so this is very different than inputting 42. So this means that f of 5 now, when the input's 5, the output is 42. Okay, really, this is what that's telling us. We solved for the input, we had the output. That's how functions work. Okay, every input's got an output. When I input 5, I get 42. So I'll leave you with B. You can give that one a shot. And again, the answers will be in that description box. And something similar might happen when we talk about this one. So I'm given that I've got two functions. F of x is equal to 3x minus 6, and that g of x is equal to 2x squared minus 3. And then we're asked to evaluate the following. So let's say that f of x, not f of x, f of negative 2 is what we're looking for. So now I know my input's negative 2, but the function is 3x minus 6. So we're going to let our input be negative 2, and we're going to plug that in. So negative 2 becomes x, that's minus 6, so that's negative 6 minus 6. This becomes negative 12. Be careful with the negative sign. Some people would see this and assume it's 0. So f of negative 2 is equal to negative 12. G of 3 then, something a little bit different, because now I have a new function. Right? I'm not using h anymore, or f anymore, I'm using g. So when the input's 3, that means 2 times 3 squared, and I'm forgetting an equal sign, so let me restart this. G of 3 equals 2 times 3 squared minus 3. 3 squared is 9, doubled is 18, so 18 minus 3, that really gets us to 15. Now, if I have to go and evaluate something where it's, one function as an input of 2 plus the value of the other function, I really have to make sure I do both parts. So I need to figure out what the output is of g when the input's 2, the output of f when its input also 2. So g at 2 is what we have to find first. Means 2 times 2 squared minus 3. So 2 squared is 4, times 2 is 8, minus 3 is 5. So when the input is 2, the output's 5. For f, when f's input is 2, we're going to do 3 times 2 minus 6. So 3 times 2 minus 6. This one is equal to 0. 3 times 2 is positive 6. Minus 6 gives us that 0. So that means when I do g with an input of 2, and I keep forgetting my face is in the way, so I'm sorry, there you go. Input's 2, there you go. Input is 2 for f, also, there you go. So when I take those values and add them together, g's input of 2 plus f with an input of 2 means I'm really doing 5 plus 0, and that gives me a value of 5. So we can take a look at functions, multiple functions at the same time, add them together as well. Now I think we messed up a sign here. I feel like it's supposed to be multiplication, so let's do that. And let's put a multiply symbol in between. Let's do that. Okay, so it should just be the dot in there. So when the input to f is negative 3, so that means we're going to have, if f's input negative 3, that equals 3 multiplied with negative 3 minus 6. That is negative 9 minus 6 for a total value of negative 15. Now when g is negative 2, that means we're going to be doing 2 times negative 2 squared minus 3. Negative 2 squared is positive 4, doubled for 8, minus 3 to get us to 5. Okay? But now, if I take the value where f's input was negative 3, multiply it with the value where g's input was negative 2, really what we're going to do is we're going to have negative 15 multiplied with that value 5 for a total value of negative 75. Okay, so there's the evaluating multiply. Now, I won't do E and F. I'm going to let you try those ones out. So these are the ones where you actually have the output now. You're solving for the input. So that value right there is the output. You were asked to actually figure out what the input is. And we did one up above. So if you need a little bit of assistance, rewind the video a little bit, and you can try that one out as well. Same thing for F. And I'll make sure you have the full key in the description. So let's take a look at just the last part here. Determining missing values using the graph. So now I can figure out, if I didn't have the equation of this function, which I don't, but I do know what its inputs are. Okay, and so I can use the graph to help here. So now I know that the input is 2. What I'm really looking for is the output. So I'm going to locate the input, which is x, the 2 value, go up till I hit the line, and that y value is the output, right? So when the input's 2, the output is 1. And I can see that very clearly from the graph. So really, when it is f at 2 is equal to 1, what that really is saying is that that is a coordinate pair of 2, 1. And I don't know why it's not letting me do what I want. There we go. Okay, so really that's a coordinate pair of 2, 1. If I look at the other one, now I know my input's -4. So now we're on the other side of the graph here. Okay, so my input's -4. I'm going to locate its value. That's going to be -2. Okay, -2. So really, again, that coordinate pair, the input being -4, the output -2. So we'll locate your input -4, output is on the graph, the y value -2. But now for C, I'm not told what the input is. I am, however, told what the output is. So if I can locate the y value of 0, the x value should be the one attached to it. Now I should only have one choice because this is a function. So if the y is 0 here, the x is also 0. Straight from my graph, this is the origin point. And the last one, if f at x is equal to 2, f of x, y value of +2, that would be over here with my y value of 2, which means my input value to get there has to be 4, the x value associated with it. Okay, so x is equal to 4. So that's how we can use our graph to help us, if remembering what inputs versus outputs mean. Okay, so just the last problem at the bottom then. This equation, the C, which I believe stands for cost, so cost in dollars, so C equals 25N plus 1,000 for a feast following an Arctic sports competition where N is the number of people attending. Describe the function, write the equation in function notation. So really they give me two variables, the cost and N, which is the number of people. So really what this is saying is it's the cost of the event. The cost of the event is a function of time. Okay, it'll cost it will cost $25 a person plus $1,000 in other fees. And so in function notation then, we're going to have to actually represent, our cost with an input beside it. So as function notation, the way it looks, cost is our function, so let's call it C. Its input is N, right? If I input the number of people, the output is going to be actually what the cost represents. So 25N plus 1,000. Okay, the only thing I can change here, the inputs are N, the number of people. The cost is what's dependent on the input, the change in number of people. If I'm asked to determine the value of C, and then I have in brackets 100, really this is the value of the cost function when the input is 100. So really this will tell me how much it costs having 100 people. So C100, it's going to represent the cost when 100 people attend. Okay, so C100 equals 25 multiplied by 100 plus 1,000. So that total cost for us is going to be 3,500. 2,500 plus 1,000 is 3,500, and I've written 25. So there you go, 3,500. Now that really is the cost, right? So that cost $3,500 for 100 people to attend. Determine the value of n when the cost function is equal to 5,000. So really we're asked to find the number of people that are going to attend if my total cost is 5,000. So this is the opposite case, right? So let's find it first. So 5,000 is the cost, and that's going to equal 25n plus 1,000. Really we're trying to find the number of people that makes this. So subtract 1,000 from both sides, and you'll see that that's 4,000 is equal to 25n. Divide both sides by 25, and 160 is equal to n. So that will tell us that the 5,000 as a cost, so the $5,000 cost, let's say the $5,000 cost means, I'm writing too fast. It means that 160 people attended. Okay, so it takes 160 people for that cost to reach 5,000. So there's a little bit of stuff on functions. Now these become super important, in future courses, especially Math 20 and 30, when you talk about functions and how to transform them and move them around your coordinate plane and all things like that. So it does come back for sure. I hope these are helping, and if you do want to work together at any point on something, follow me on Twitter, follow me on Instagram, leave me a comment, send me an email, all of those things, and I hope that you do find these worthwhile, beneficial. So until next time, take care and stay safe.